can everyone? Does this work? Can everyone hear me? Like, okay, yes, obviously, I'm not online. Okay. Yeah. So, firstly, if you didn't already scan the attendance, which you have because I manually went around to everyone to ask them to scan the attendance, but please scan that now. Yeah. And okay, so if you guys are already confident with content, you can move on to the VJudge. The VJudge is just a set of problems. Certain people from the back row have already attempted the problems. So yeah, they tested the problems. They look pretty fine. So if you want to join the link, you can either follow along with the workshop, or you can hop on the VJudge straight away, and then we'll give you time at the end to work on some problems on the VJudge as well, and we'll go around and help you guys, right? So that's the general idea. Can you write the VJudge link on the board so that it's it's like, wow, that's tiny. That's tiny. That's not big enough. Wait. There's a rage.
That's what she said.
Okay, the code is what matters, right? 797040. And the password is just CPM sock, right? If you guys can't access it, let me know. You do need an account. Should be pretty simple.
Righty, we're going to start with an intro topic into ranges and pointers. We'll start with a demo problem. All right, going viral. The marketing team has accidentally granted you access to the CPM Sock Instagram account. You've been putting out banger reels once a day for the past N days, with the ith reel accruing some number of likes, AI, which may be negative. To see if you have a shot at virality, the marketing team would like to find the highest average number of likes over any K-day period, where K is from 1 to N, and K is a fixed number that's given to you. Since the marketing team doesn't like to program, but you ostensibly do, they'd like you to solve this problem for them. All right, is everyone good with the problem statement? All right, okay, one observation. If we start on day I, like this is just our definition of the average. Important thing is that the K is gonna be there no matter which K-day interval you pick, right? Or the 1 over K. So we can basically just ignore the 1 over K and find the maximum sum over any K-day interval. And then we would just divide that result by K at the end, right? Yeah, so with this, you can find a really easy, straightforward, naive solution. For each possible start day from 1 to N plus 1 minus K, which is like the latest possible start day, we just consider all the days in that K-day interval, add it to some total, and then just take the biggest total and divide by K. Cool. The issue with that is time complexity is pretty bad. We have to do like that many start points and add K different stuff together. In the worst case, this is N squared. Right? Can we do better? Another observation we can make is if you've got consecutive start days, the K-day period is pretty similar. Yeah, so for example, if you've got a 901 day period from 100 to 1,000, if we kind of shift that period over to 101, 1,001, they're pretty similar, right? So even though it's a really big range, the only things that really changed were that we added 1,001 to the end of it, and we removed day 100 from the start of it, right? So this is a really useful observation because theoretically, we could share some information between these two. Yeah, so this is where we introduce the idea of a sliding window. So in this context, a window is just some subarray or range over an array. And if we want to find some property of this range, so for example, in this problem, we're trying to find the sum over that range, or average. If we can perform the following, being shift the right endpoint to the right, hopefully that makes sense. We're just moving the window a little bit right. and we're kind of just using the previous information. And similarly, we can move the left point 1 unit right using that same information. Then it's possible for us to sort of slide the window we care about in the same time complexity that it takes to do those two small operations. Does that make sense to everybody? Do you understand that idea? Cool. All right, so then we can use this idea for our solution. If we start with just the first window, meaning it starts from day 1, it'll just be like the sum of the first k days, which we can just do. And then now, every time we want to slide our window along, all we have to consider is just, okay, it looks a bit complicated, but it's not really. You're just currently considering this interval, and we now want to add this new day. So then you just have to add the value, the number of likes you got on that next day. And similarly, we also have to shift the left side of the window in. And since we're kind of removing that day from consideration, you want to subtract that value back off. Right? Now, after doing all this, we just want to find the biggest of those sums of that k-day period, and then we just divide our answer by k, and that'll be our answer. Right? Yeah, so time complexity for this solution is a lot better because I guess creating the first window is order k, but then after that, finding each of the other sliding windows only takes constant time if we use the information from our previous window, right? So that becomes order n. Yay. Right? Cool. That's the sliding window technique. Now we have a new problem. Some excellent sums. You're at the grocery store and would like to buy some eggs. There are n eggs in a line where the ith egg contains xi yolks within, which can be from 1 to 1,000,000. And this is written on the outside of the egg. So you are aware of which eggs are good. You would like to prepare a feast that requires exactly k egg yolks. No more, no less. To acquire your eggs, you ask Austin, that guy, to go to egg number number I, and you ask Matthew, that guy, to go to egg number J. And you just assume that J is at least I. The two of them then run towards each other, grabbing all the eggs along the way, including at their starting positions. Do you guys want to do a demonstration? Yeah, good job. So if they picked up k eggs, we're happy because we can make our feast. But if they took any less, it's bad. And if they took any more, that's also bad. We don't want to waste any food. Okay, the question is, how many different possible pairs for like their positions will result in us obtaining k eggs? Right? And some constraints. N is up to 1,000,000. Xi is also up to 1,000,000. And k, your target egg yolk, is up to 1,000,000,000,000. Right? Yeah. Okay. Here are some sort of straightforward solutions you might think of. Okay, so the first one, you can just consider every possible option for I and j, and then just check what that sum is and see if it's equal to k. So we have n squared different subarrays, or like order n squared, and finding the sum of each one of those naively would take order n, which gives us n cubed, which obviously is not enough to pass. People are familiar with time complexity and understanding what passes, right? Yeah, cool. Like usually you want the number to be about 1e8 or a bit less. Yeah. Okay, so now second solution, which is probably a natural one to think of. If we started Austin at position I, and then Matthew at position J, then if we moved Matthew just 1 over, we don't have to recompute the entire sum, right? It's sort of similar to the sliding window idea. You can just keep a running sum as you go and update that on the fly, which is nice. So in this case, we're going to still consider n squared different subarrays, but the sum is computed in order 1 for each one of those because you're just kind of using the information from before. But this is still n squared, so while it's better, it's not good enough. Okay, so now we're going to make some observations. Okay, so first of all, let's pretend we have some solution ij. So if Austin starts over here and Matthew starts over here, they're going to collect k in between them. The question now is, if I told you there was some other solution, can I use a white marker? Yeah. Yeah, right. Sure.
Can everyone see like this board?
Yeah, okay, cool. So like if we have our egg, if we had a solution here to here, where the sum of these three was equal to k. If I told you there was a new solution which started on this one, can we make any observations about where it has to end? Yeah, after j, right? It's not possible for it to start at or before j, because if that was the case, that would tell us that this is equal to k, which would mean that the original I to j had to be bigger than k, but we know that that's not true. So from this, we can see that if we start at a later point, we have to also end at a later point, which might be this one, might be further on. Okay. Yeah, you can see that we have to have the endpoint be further on. And this is basically the condition that we need for running a two-pointer algorithm. Basically, 2 pointers is similar to how we're tracking a pointer for Austin and one for Matthew. If we're trying to find some subarrays of some array, which meet a property, and we can show that for any two solutions, we kind of have to shift both of them together. Then we can use a two-pointer algorithm, and basically the way that works is you start by setting them both to 1, so I and j are both over there, and then pretty much while the ith one is less than n, so kind of just iterating over each one, you're going to basically just push j as far to the right as you can until like there's an issue, and then if you push it to the furthest it could be, we either like found a solution or we didn't. But after that, if we kind of consider the next I, we know that the j has to still be at least that position, or possibly further. But it can't go back, is the important criterion.
So just checking. So
Yep.
if there's x with negative yolks, and this would work.
Yes, this wouldn't work, because it is possible that by adding a negative guy over there, by skipping a negative guy, you have to come in. So yeah, so the positive yoke is very important.
What if you have an egg with 0 yolks?
Anyone have an idea for this? What happens if there's 0 yolks? Does this cause problems? Yeah, it shouldn't really cause a problem. Only thing is just this j bar bigger than j just becomes j bar bigger than or equal to j, right? But that's still okay, because it just means as long as we're never moving it backwards, that's still okay. Yeah, good question, Matthew. All right, so here's our two-pointer solution for excellent sums. Basically, just as described, you set them both to 1 while I is less than the the end. While the current sum is too small, then you definitely have to consider checking further. Right? So while it's too small, we increment j, and obviously update the new running sum. Obviously, do not push Matthew past the last egg. Yep. And then once the sum reaches k or higher, you know that there's never any solution further down, so you can stop there. And you either have a solution or you don't, just based on if the sum is equal to k. But after this, we know that when we increment I, and also remember to update the running sum by subtracting what used to be there. After we increment I, we can use the same j and just continue pushing that one further. Right? So we don't have to redo it. Yeah, so kind of by the two-pointer property that we have, we're never going to miss any solutions. And in terms of complexity, While there is still like a double while loop, which is often scary because it can mean like n squared stuff happening, the main observation you can make is that the pointer I and pointer j, both of those increment at most n times, right? Because they only ever go forwards from the start of the array to the end of the array. And all the other stuff we're doing along the way is also constant time. So this means we're able to find all the valid subarrays, but in order n, which is suitable for this question. Right? Cool. Does that make sense to people? Yeah.
How would you implement this?
How would you implement this? That's like pretty much the pseudocode. Like alternatively for the I, you don't have to use a while loop because like you can see we're just doing while I less than n and then increment at the end. So like you could also just do it with a for loop. I don't know, I just think it's a bit easier to think about for the 2-pointer idea if you treat them like similarly. But yeah, you can just chuck I into a for loop and then have j be some kind of global to the for loop and just increment that each time. Right? Okay, here's another problem. See if you can use the techniques to have an answer for this one. No longer viral. After failing to go viral online, you've decided to make friends the old-fashioned way. For each of the past n days, you've spoken to one person numbered xi. Note you can speak to the same person on different days. You would like to find the largest number of consecutive days in which you did not speak to the same person more than once. Presumably this is good because you're talking to people. Right? And our constraints are n is up to 1,000,000, the people numbers are up to n, and what is k? K, I think that's from an old question, ignore k. Right, some thoughts. I guess one natural idea is to consider every possible starting point, because remember we're trying to find like a subarray. So if we had some starting point, what can we do from there? For a particular start point, you can imagine there's going to be some biggest end point where everyone is distinct in that range. All right? Because if there wasn't one, you would just, well, like, if everyone was distinct, you could potentially extend it further. But as soon as you find someone that matches someone previously, you can't extend any further because that matching will stay in any bigger range as well. Right? Yeah. Okay, so now. Oh, okay. Okay, so now we're going to start thinking. If the furthest endpoint for start date I is j, so that's the furthest endpoint where everyone's distinct in between, what can you say about the furthest endpoint for start day I plus 1? Any ideas? Yeah. Okay.
Wait, while people are thinking, let me clear this board.
Okay.
Does everyone still remember the problem? Does everyone still remember the problem?
Yeah.
Yes.
With no duplicates.
With no duplicates.
Why is the rubbing so bad?
Did you guys use a micro marker or a permanent marker? That was a.
Well, yeah, most of this wasn't us.
We should not mark that. Stuff that was you guys also is rubbing out.
Oh my god. Wow, this is really awful, isn't it?
Any endpoint. It's like abstracting I plus 1 is already included in the range. So by moving it forward, you're actually just excluding an element. So the greatest, the furthest endpoint must be at least.
Oh, endpoint. Yeah, it's, yeah, like the same size, but like just one. Yeah.
Oh, got an idea.
Can you give me more time to think?
Wait, we should go like back to the problem. Yep. Yeah, you guys can read the problem.
Yeah, this is the idea.
Just that it must be greater than or equal to j.
Okay. Do you have any justification or like where that comes from?
So like moving the start point to the right
Mhm.
would only like
Pretty much exactly the right idea. Is there a good marker? Surely that one's fine, right?
This is the one that we saw.
Yeah, so basically the observation is if we've got some I and some J where everything from here is distinct, if we considered I plus 1, it's pretty obvious that everything from here is also distinct, right? Because if we had like a copy, it would have been a copy in the original thing as well. And so that means we can definitely do at least J. And exactly as, what's your name? Martin, nice to meet you. Exactly as Martin mentioned, it's possible that by freeing up this guy, he could go even further, right? So because we have this property where if I gets bigger, J doesn't get smaller, we can use our two-pointer approach. Okay, this is basically what we did. Right, so kind of our standard two-pointer solution, set the two of them to 1 initially, and then while I is less than or equal to n, or you can do it with a for loop. While the kind of next option isn't already seen, we kind of move it forward, and obviously don't go past n. And if we have a kind of valid solution that works right now, you can record that size, which is like j minus I plus 1, so that's how many days you went without any duplicates. And yeah, we then just increment I, do this for every possible start day, and then from that we can just take the largest such interval. Yeah, so I guess the only thing that's missing in this algorithm is how would we check if kind of the new element has already been seen in this array. So obviously we don't want to loop through it. Any ideas from anybody?
So like we make an array
Mm-hmm.
like x1 from like all the possible person
Yep.
can appear, and then like check 1 and or 0 like if they
Mhm.
appear or not.
Yep.
And then like if we move one, like move I by 1,
Yep.
we just remove that section.
Yep.
And, like, yeah.
Sounds pretty good. So the idea suggested by, what was your name, sorry?
Yevin.
Yevin? The idea suggested by Yevin was we can basically keep an array, which is like 1 or 0, or like a Boolean array, where we mark them with a 1 if they are in the interval. So we can do that whenever we extend, we set them to 1. And whenever we contract, we mark them as unseen, so set them to 0. And obviously we're not allowed to extend if the new person is already set to 1. Right? Cool. And that's okay because we've got our people numbers are at most n, which is also 1e6. Just a little bonus question. We don't, actually probably someone can do it. If our x numbers are unbounded, well, not, up to 1e9, so like the friend numbers could be really, really big, right? So we can't keep an array of a billion stuff. Anyone know like a data structure that could do this? Yeah.
You could use a hash map, but is there can this many inputs not appear? Like, is there a problem with?
No, hash map is fine. Yeah, so like you basically just have a key being the person's number, and then the value is just whether they're seen or not.
In the worst case, it would actually be worse though, right? Because like your hash map would just get full of like 9 elements.
No, because the people numbers can go up to 1e9, but there's still at most 1e6 days.
Okay.
So it's just you have kind of scattered entries, but still have at most 1 million of them, even though the values can go up to 1 billion. Cool. I think we're covering hash maps in more detail afterwards. Okay. Yep. Complexity again. Both I and j increment at most n times because they never move backwards. Everything else we're doing is order 1, either with the scene array or the hash map. And so our overall algorithm is going to be order n, which is good. Right. Cool. Okay. Next section is on data structures by. Yeah. All right. Okay. Thank you guys.
Okay, I have not seen the slides for this section, but let's find out together then. What is a data structure? Okay. Data structures are objects that store data and perform actions on said data. And normally we talk in terms of, let me guess, queries and updates. Look, queries and updates. blah, 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 queries and updates. If you use a hash map, for example, an update could be put an element into the hash map or set the value of a key equal to a value. A query could be what's the value at a certain key, right? And if we have a good data structure, we want it to do the queries and the updates relatively quickly. Normally that means O of 1, O of log n, something like that. Yes, speed at which they perform operations, including queries and updates. Some examples, I think these are questions, right? Open-ended questions. You guys can answer these. What's a data structure which takes in n ordered integers and you can set in O of 1 and you can query in O of 1? Any ideas?
Does it preserve the order? Or
Yes.
oh, in like the I.
Yeah.
What kind of thing?
Okay.
Yes.
I mean, we're giving you guys time, right?
For a bit on the rage bait.
Thoughts?
I promise you've already learnt it.
Like it's just an array, right? But
Yes.
it would be mind-numbingly bad.
Yes, it is just an array. Array you can do O of 1, O of 1. Very good. What's a data structure which which supports the following? I think you might have had to take 2521 to know this one, right? Yeah. Or if you'd used this before. You can insert an integer x in log of n, you can query in O of 1, and you can remove in log of n. Yes? Binary search tree, yes?
Is it like
I think
AVL?
AVL tree, I think there are a bunch of them that work, right? AVL, red, black tree. Oh, heap also is good. Yeah? AVL tree also works, so everything's correct. Okay. I think that we have a one challenge one here. Oh. Okay. This is something that you will learn in the future, probably at the end of the term. But you can query in a log of n, you can insert in log of n, you can reverse a subarray in log of n, and you can add an arithmetic sequence in log of n, which means like 2, 4, 6, 8, stuff like that. Anyone know what this is called? Yes?
Can I have more time? Is this a range tree?
It is a range tree. Yes.
Segment tree?
You can't reverse a range in a second.
Oh no. Okay. I know which this one is.
Yeah.
If I give you guys 8 weeks of time, you'll be able to answer this question.
Might be a few more than 8 weeks.
Okay. All right. Oh, okay. So this is another data structure that allows us to do range sums. It's called a range sum thing because like arrange something. Get it? I didn't come up with the joke. Okay. A problem. Rob the racist. Okay. Thank you. I came up with it. Thanks. Okay. Rob is a racist. He likes running races. Okay. A race consists of n sections, each of which is a certain number of kilometers long. Amateur racists like Bob don't need to run the entire race. They can just run some range of the race. So, for example, just like the eggs problem, right? Some I to j or L to R here. Unfortunately, Rob is also a racist. And I should have left this for the competition. Because he's a racist, he keeps changing his mind about which sections he wants to run to avoid certain types of people. He has Q questions, with the I question asking for the total distance of sections AI to BI. Maybe he has some limit that he can run. And you want to help Rob answer his questions. Maybe you shouldn't be helping him because he's a racist. And part 1, we can solve this in O of n q time, pretty slow. And part 2, we can try to solve this in O of n plus q time. By the way, if you guys do this problem on VJudge, it's called like a really boring name and the flavor text is really boring. So you better thank me for reflavoring it. Okay, anyone have an idea for the O of NQ solution? Very, very slow solution. You were too busy reading the flavor text.
It's very flavorful.
Thank you. Yes, or like it was a question. I reflavored it. I just gave it some,
Total distance.
Yes, exactly. For each range, you can just sum up all of the values for loop. So brute force, we can just sum up every value using a for loop, and that's O of NQ, because in the worst case, Rob is annoying and he keeps asking for the entire subarray or the entire array. Okay, how do we answer the queries more quickly? And the key here is that we want to do some sort of pre-computation. And I'll give you guys a geometric hint. So we want to answer questions about how long a certain range is, and we want to sort of compose that range out of two other ranges. So have a look at this range here. Imagine this is the entire race, and our sections are 3, 3, 4, 5, etc. How could we compose that segment of races or of ranges using two other ranges? And ideally, those two other ranges should have the same starting point. Prefix sum? Okay. So which two other ranges would we be using?
So you mean composed from two other ranges itself?
Yeah, we want to get the distance of this range using the distance of two other ranges.
You could just, if you know the whole sum,
Mm-hmm.
then you can just subtract the endpoints, right?
Yes, you can subtract. I'll have a visual here. Yes, yes. So you can take, if you pre-compute the values of those ranges, you can subtract the area or the distance of the yellow range from the distance of the blue range to get the distance of the green range. And the useful thing is that the blue and yellow ranges both start at that first section of the race, so that it allows you to pre-compute quickly. Okay, so this structure, for those of you who don't know, is called a prefix sum. So every range, I used a bit of math notation here, but every range can be expressed as the sum of two different ranges, a larger one and a smaller one. So if we pre-compute the values of all those ranges that start from the first section, we can get the sum of any range in O of 1. Everybody understand? Yep. Okay, so normally we can just pre-compute the prefix sum using a single for loop, because the value of the prefix sum at I is just the prefix sum at I minus 1 plus whatever the array is at I, and therefore you can answer his questions in constant time. So our time complexity goes from O of NQ to O of N plus O of Q. Answer every question. All right. Okay, so we've learned prefix sums. You know what they are. Now here's a slightly harder application. Unfortunately, I did not write the flavor text for this problem. It's a bit more boring. It's Farmer John. He has N cows that are standing in a line. Each cow has an ID. It's like a name. And he wants to take a photo of some group of cows that are consecutive, but he only can take a photo if their IDs sum to a multiple of 7, because he has PTSD of 1 to 6. And the question is, determine the largest group that can be in the photograph. Farmer John's also a programmer, so he wants to do it in O of N. Any ideas? Yeah, same thing mod 7. So you want to find the longest subarray that has a sum that is concurrent to 0 mod 7, right? So how would you do that? How would you find the longest subarray specifically? Yep.
Do the prefix sum like that, and then compute, we have pointer, and then go through the array, and then compute the prefix sum minus the sum of elements we have, and then
Mm-hmm. So yes, if we have an L and R, yes, so you want to have prefix of R minus prefix of L, and you want to make that as big as possible. So I think, as you said, loop through the array, and for a certain R, you want to find the L that was furthest away from that R, right?
yeah.
Furthest back. So yes.
Yeah, in this case, we know that the numbers are 1 to 6,
Mhm.
and they add up to 7, right? So you can
Yep.
you can just check all contiguous arrays of length 1, then
Uh,
That's still the thing.
I think you've misunderstood the problem slightly. Because so the photographs aren't of size 1 to 6, as in the photographs can't be divisible by 1, 2, 3, 4, 5, or 6. So the ranges can be like, actually, let me put up there's a sample case, sorry. For example, on the board there, the answer is 5 because the subarray that starts at 5 and ends at 14 has a sum of something that's divisible by 7.
It's like mod 7. Okay.
Yes.
For a segment or subarray to be valid, the start and end needs to have the exact same prefix on mod 7.
Yes, yes.
So for every single, like from 0 to 6, you just check where the first 0 is and where the last 0 is to find the difference, and then do that 6 times.
Yes, exactly. So because it's mod 7, we know that the first, like the prefix sum of the right end and the prefix sum of the left end minus 1 must be congruent mod 7, right? They must be the same, have the same remainder when divided by 7. So to find the biggest subarray for every congruence value, you can simply find the first index and the last index satisfies that, subtract them. Yes, it's just the last minus first index, and because there are only 7 possible values, mod 7, that's O of 1, so checking is O of n total. So Farmer John is happy. Okay, everybody understand that problem? All right. I think that's the end of my section. Austin, take over.
Hi. So hope you found that instructive. And so my section is about linked lists. So you might remember if you ever did 1511, you would have learned something called linked lists. Has everyone done the course? I haven't. Thank you. Neither have I. So has anyone else? I assume a majority of people have heard of at least what a linked list is. And so let's start with not linked lists. Let's start with arrays, right? So we all know what arrays are. And so I want to ask a bunch of operations that you can perform on arrays, and you're going to give me the time complexity of those operations. So the first one, what's the time complexity of adding an element to the end of an array? O(n). Assume resizing takes constant time, which is true, I guess. You allocate. How do you resize in constant time? You just point your memory to, like, you'll point it to a different memory address, right? Who cares? I mean, in competitive programming anyway, we don't really care about the actual operations themselves. We care about it like we count in bit operations basically. So, yeah. Did you have a?
Oh yeah, isn't it O1?
Yes. Why?
Because we can just directly, like, if we know what the index is, we can just directly go to the index and then like put it.
Yep. Exactly. Right. So at the end of an array, it's O1, right? And let's give this operation a name, right? Let's call it pushback, right? Because we're pushing something to the back of the array, right? Fairly intuitive. Okay. So what about this? What about this operation where we delete the last element of the array? Does anyone have a idea for what time complexity this would be? Yeah, also O of 1. Why is that? Yeah, you set it to null, right? Exactly. And you assumedly you decrement the count or something, or the size. Yep. And so we call this pop back because you're popping it off the end of the array, right? You're popping off the back. What's the time complexity of adding an element to the start of an array? Oh, why is that?
Because we need to ship all.
Yes, exactly, right? So part of the power of an array is if you give it an index, it should immediately be able to tell you what element is at that index. So if we add something to the start of an array, we will have to re-index every element, right? We need to set every element to have an index of that previous one plus 1, right? So we end up with an O of n, and let's call this operation push front, right? And I mean, you can probably guess what the time complexity of deleting the first element is. It should also be O(n), right? Because you need to move through the array and then decrement all the indices, right? And so this is O(n), right? Yep.
But what if we just make another pointer that points to array 1 and then call this is a new array.
To create the array, that would take O of n as well. So you can set the reference of the array to point to the new array, but you'd have to create the new array, right? And that takes O of n anyway. Yeah. So does everyone understand? It's like fairly intuitive. Okay. So you might have heard of this data structure called linked lists. Unfortunately, I haven't. So I don't actually know what linked lists are. So we're not gonna look at these today, right? Instead, I realize like I don't actually need to care what a linked list is, right? Because turns out C++ is really nice and implements them for me pretty much, right? And so this comes to the part of the lecture where it's helpful if you already know a bit of C++. If you don't, it's okay. We'll generally step through how you would use this. C++ syntax is pretty similar to C, but for C++, you don't have to implement a linked list from scratch, thank God. They have several built-in data structures and algorithms packaged in something called a standard library, right? And so you don't actually have to implement the pointer like garbage that is like linked lists, right? So if you are using a GNU compiler like G++, then at the beginning, you might remember include from when you did C. You would include like stdio or something, .h. In C++, there's this really useful header. It's just bits / std c++.h. Some people don't like including namespace std. I don't care. I just put that there, right? And this should import most of the standard library, right? And so most of the things which we'll talk about in this lecture, in fact, all of the things will be in that library. But if you don't use a GNU compiler, you can import everything manually, right? For example, you could import IOStream, you could import vector, you could import set, you could import like whatever, right? And so you import all the containers by themselves, right? And then you include namespace std or use namespace std. So we're going to look at this structure called a queue. Has everyone heard of a queue already? Yeah. Okay, 2521 did it. Great. Okay, so this will be revision, right? So a queue is a data structure which supports pop front and push back in O of 1. So what that means is it's a data structure. It looks like an array, right? But you can add something to the front of it in O of 1. Sorry, you can take something from the front of it in O of 1, and you can add something to the back of it in O of 1. So no, this is just a single-ended queue, right? So like the helpful visualization here is like imagine you have like a queue of people, right? Like a line of people. And basically what a queue does is it allows you to support two operations quickly, right? The first one is insert a person into the queue. And like they will walk to the front of the queue, right? Where they'll wait. And then, maybe you add some more people, like person 3, person like 2, right? And then let's say they get called on, right? Queue supports an operation which allows you to take the first guy you inserted out, right? And so queue is basically like this sort of, it literally models a queue, right? And you can put things in from the back and take things out from the front really quickly, right? And you can also figure out what is this element. You can ask the queue, what is this element? Does this make sense, everyone? Yep. And so this is how a queue is used in C++. So you can see, firstly, I'm using my header. I'm including the stuff that I care about. And then I'm creating this container, which is called a queue, right? And you can see like the syntax is a bit strange, but it's just making a queue of integers, right? And then, I commented what the queue will look like after every operation, but you can call push, which will add something to the queue, push, which will add something to the queue, and then maybe I want to peek what is the front value. That will be 1, right? Because 1's at the front of the queue. And then I'll pop, which takes 1 out, right? It takes the first thing out. Does that make sense to everyone? Yep. And these are often called FIFO structures. You might have heard of this term. FIFO, first in, first out. Nobody really says it anymore. Okay, stacks are pretty much an alternative. They're sort of a different structure. And what they do is they support pop back and push back in O of 1. And what does that look like? You can think of a stack as quite literally like a stack of blocks, right? And then so you insert something inside, and it adds like this. Now, if you want to take something out from the stack, you can't take from the bottom, right? Because it'll like topple everything. So a stack allows you to take something from the front. And you might think, hey, isn't pop back and push back in O of 1 exactly what a vector does? Correct. So stacks are just worse vectors, right? And these are referred to as LIFO structures, right? Last in, first out, right? The last thing you put in is the first thing you take out, right? Fairly intuitive. And this is how you would just use a stack. Why would you use a stack over a vector? Some people just always use vectors. Personally, I think if you're doing any data structures problem, you should use the data structure which isn't overkill, right? Like for example, if you're using a stack, you don't need random access. You don't need to ask what is the X element in the stack. Then you would use a stack, right? If you needed to ask that question, then you'd use a vector. I think it keeps your code relatively tidy and also helps people, especially if you're working in the team, it helps your people figure out, you're actually using a stack, not just a vector, right? So it's very helpful in that regard. It's like a standard, which generally I stick by. You can just use a vector, I don't really care, right? And so this is how you would use a stack, fairly simple. There's still a problem though, right? And you might remember when you did linked lists or when you didn't do linked lists, you might remember linked lists seem to support adding things front and back and everywhere and removing things from the front and back all in O of 1, right? Unfortunately, we have 2 containers here which don't support all 4 of those operations in O of 1, right? And so that's the issue, right? So it turns out C++ has this covered for you, and it's called the deck, right? And the deck, it's pronounced deck, by the way. Don't say it's a DQ. That is incorrect. Rage bait. Okay, but deck stands for double-ended Q, right? That's what the D and E stand for. I made this up, by the way. I don't buy that this is true, but it looks probably true, right? So this is how you use the deck. Now decks are really OP for some reason. I'm not entirely sure how they're implemented in C++. But what they allow you to do is they allow you to push back, push front, pop back, and pop front, all in O of 1. They allow you to peek at the front and back elements in O of 1. They also allow you to peek at any item inside in O of 1. I'm not sure how it does that. Like, how does it do that? Yeah?
It's all like
A vector.
yeah, they're all like a vector. They're all just double-ended arrays basically. So you have like an array that if you
Yep.
reach the end,
Yep.
it's like loops round back to the start.
So like a ring buffer.
Yeah, ring buffer. Yeah, and then if you just expose like one end, then it's a stack. If you just expose the other end, it's a queue. If you expose both ends, it's a DQ.
Do you buy that?
Isn't it like a
But
trunked
I
vector?
think you can, the standard library, I don't think it defines the data structure that implements it, so you could also like probably call the standard library and
You could probably ask it to do a different container, right? Yeah, you can ask it to do a different container. It doesn't really matter, right? Like, I don't really care how it works as long as I can use it in my algorithm, right? Wait, this is like factually correct, right? Okay, like maybe if you were doing 2521, you would have learned something called like abstract data types or something, ADTs. You don't actually care about like how it's implemented under the hood. You just need to be able to call certain functions and it works, right? So does anyone have any questions? Yes.
What is the difference between vector and deck?
Deck. A vector, if you remember, okay, if you remember, a vector, if you remove something from the front of a vector, it takes O of n, right? Because you need to shift all the elements to the right. Deck doesn't need this. So deck, if you remove it from the front, it takes O of 1, right? So it's extra like speedy at changing all its values as long as you're just removing from the front and back or adding. Yep.
I'm wondering why do we still have this front back shift problem, right? Can we not just make an array? So like normally the vector has a length and a capacity.
Yes.
Right? And when you go over the capacity, it does the like reallocates to 2x bigger.
Right. Yes.
So you have a more
Correct.
Why don't we just do that, but on both ends? It's still the same runtime complexity, and now you get to remove and add to the front and back without reinvesting.
It's the same complexity, but you're doing more work, so it's just slower.
Yeah,
It's like you get like constant like
I mean, like you don't have to do them at the same time, but like it would be exactly the same, right?
Because what if you add like one to one end and then you expand that end and then you want to add to the back, then you're also going to re-expand even though you have half the space.
Yeah.
So you're
But
wasting like memory and like doing
still,
more.
like amortized, it's fine, right?
Yeah, but like it's like from a practical point of view.
I mean the whole point is if you want to use a vector, you only need to use like a single type of operation, right? So it's better that they like narrow the implementation rather than having like a does everything, but
What I'm
you know
describing might just actually
be a deck,
implementation
right?
of a
Yeah,
deck.
yeah. Like it might just be right. Does anyone have any questions regarding the? Okay, I'll assume no. Okay, so we'll do a sample problem. This problem you might have seen before. It's a pretty famous problem. It's called bracket sequences. And so there's a definition of bracket sequences here. It's pretty complicated, I guess. It's like if A is a valid bracket sequence, you can add a pair of brackets onto it. Likewise, you can concatenate two valid bracket sequences, or the empty string is a valid bracket sequence, and you want to figure out, given a string, what is like whether or not it's a valid bracket sequence. The intuitive way of thinking about whether a bracket sequence is valid is if you write it in your IDE, it will be all good, right? Like all the brackets match, right? Like for example, this is great, right? Like your IDE will be yay, happy, right? Here, like why are you enclosing a single like square bracket, right? Like you're getting fried by your your IDE, right? Or like your IntelliSense or whatever, right? So pretty much that's how you want to intuitively think about bracket sequences. I'll give you guys like maybe like 30 seconds to think about this problem. Stack. Okay. Does anyone else need more time to think about this problem? No. Yeah? Okay. Huh?
Last time.
Okay.
Like did it as a lecture example a few weeks ago.
Yeah, okay, so does anyone... Okay, so actually that means like I'm basically as good as a 2521 lecturer, right? Because I like came up with I re-derived the exact same like... So I might as well just be like lecturing 2521, right? So wait, does anyone still need time to answer this problem? Okay, well, I mean, pretty much. The idea is you want to match from the inside out, right? So you want to eliminate pairs from the inside out. For example, in this case, like these two brackets, they can just be removed, right? Or like these brackets can be removed, and then these brackets, and then these brackets. And when it reduces to an empty sequence, you know it's valid, right? But for example, for something which can't be reduced, you get to a state where there are no more like adjacent bracket pairs, right? There are no more. There's a state where a closed bracket is not adjacent to an open bracket of the same type, and that's how we know it's not possible, right? So this gives us a solution, and basically each closing bracket can only match validly to at most one opening bracket, right? This is just by definition of what it means for a bracket to match, right? Every closing bracket needs to match with exactly one opening bracket, right? So this actually happens to be the nearest opening bracket of the same type. And you can probably prove this. It seems fairly obvious. Yeah. Does anyone think that this is not obvious? Yeah?
Wait, the nearest opening bracket of the same type?
Nearest to the left.
I assume that's after you've already eliminated stuff on the inside.
Yes.
Yeah,
Yes, after you've eliminated something from the inside. Yes, yes. Does that make sense? So what we can do is we can compute the nearest opening bracket by maintaining a stack. And the idea is when we encounter an opening bracket, we add it to a stack, right? And then when we encounter a closing bracket, firstly, if the top of the stack is a matching open bracket, we can eliminate this pair, right? Because that closing bracket has to match to something, right? And it needs to match to the nearest, the nearest opening bracket that we've already reduced, right? So if the top of the stack is a matching open bracket, we can eliminate. But if it's not, then we know that there's no opening bracket of the same type. We cannot match this, right? So eliminate just means pop off the top of the stack, right? And then if we can't match, we should just return false. Does that make sense, everyone? And so basically the idea is if the stack is empty at the end, S is valid. Otherwise, if there's still opening brackets inside, it means there are still unmatched open brackets, and it should be not valid. Does that make sense as a solution? Yep. And this should be O of n, but I didn't really care, right? Okay, time to introduce a new idea, a more interesting thing you can do with stacks. So this problem called sumo wrestling. The idea is there are n sumo wrestlers, right? And the ith one has a strength, AI. Right, so each sumo wrestler has a strength. And they're thrown into the ring one by one in order from 1 to n. And so when a sumo wrestler enters the ring, it throws out all of the strictly weaker sumo wrestlers, right, that are currently in the ring. And then what it does is it just stays there, right? It just sits there, right? Its job is done. It doesn't throw out any more sumo wrestlers. Even if more come in the ring, it doesn't give a crap, right? And so basically the idea is for each wrestler, you want to compute how many people they throw out, Yeah. Sure. And you got some subtasks. I wrote some subtasks. I didn't really pay attention to whether they were useful or not, but there are some subtasks there. So does anyone want to think about this problem, or should I? I mean, I'll give you guys like 30 seconds to think about it.
Yeah, maybe it's stack problem.
Wow, excellent observation. Yeah,
I think you make a stack.
excellent. That's true. The solution does involve a stack. Yeah.
I think you add sumo wrestlers to the stack.
That is a true statement. You do in fact add sumo. I mean, you add integers to the stack, but yes, sumo wrestlers. Yep. Sure. What does that mean? Interesting question. Huh?
Can I solve it using binary search tree and then with stack?
Explain how you would do that.
I mean, I was thinking of something similar to I did for a last few weeks.
Yep.
I can't explain now.
Oh.
Like sense of yeah, like if someone is given, like we sort, like make a tree
Yes.
and then like we search through the tree
Yep.
and then we put the like all the left subtrees
Yep.
to the stack and then like pop it.
I mean, you don't need a stack. You can just pop it, right?
Oh, okay.
Yeah. So I buy that.
Oh.
Yeah.
Whenever we add a sumo wrestler to the stack,
Yep.
we pop all of the weaker sumo wrestlers.
Okay. Interesting idea. Why is that? What does that do?
I guess you might. Oh wait, hold up. I'm stupid. You need to also bubble up the weaker ones to the top, I guess. So you want to have a monotonic stack, right?
Interesting. Yep.
I think it'll always be Noah from the strongest because
Yes. And why would you say that?
Yeah.
Sure. Yes. Okay. So that was a crucial observation, and like now I should probably share the solution, right? So let's see what happens when we simulate the process. So what we're gonna do is this is like just like some initial thoughts about the problem, right? So we're gonna maintain some list L of sumo wrestlers which are currently in the ring, and for each sumo wrestler, we're gonna count the number of weaker wrestlers in the list, and we're gonna remove them, right? So we're gonna iterate through the list every time we add a sumo wrestler, and we're gonna see, is this sumo wrestler weaker? And if it is, we're gonna remove them. And then we're gonna add it to the list L, right? And so this process is O of L, size of L, because we have to check all the elements in L, right? We need to so go through. We might need to, you can remove all of them in one go, so it's still O of L. The total complexity of this is O of N squared, but we can do better, right? So we want to optimize the part where we're searching through the list, right? That seems like a pretty natural part to optimize, because we're always gonna have to go through every sumo wrestler. So how are we gonna do that? Well, I was gonna, okay, do you think this provides annotation? I don't know. So basically, let's draw each wrestler's strength as a bar. And I mean, okay, good luck seeing this. But the idea is, let's draw the sumo wrestlers as like a bar, right? And say, for example, the bar looks, as in the first sumo wrestler that you enter into the ring looks like this. If we add another sumo wrestler, for example, I mean, let's say we added a bunch or whatever, and we added, this is actually a bad idea. I should do like this. Let's say we had a bunch of sumo wrestlers in the current list, and then we added a new sumo wrestler. Well, what do we notice, right? Basically, we notice that this sumo wrestler will sort of eat up all of these sumo wrestlers, and then stop once it gets to a sumo wrestler of higher height, right? Because that corresponds to the sumo wrestler having being weaker, right? So it's not able to throw it out. And so you can conclude via certain methods, i.e. induction, that is true. But you can conclude that you only need to remove a suffix of the things which you added, right? And that's true because everything before is just going to be in descending order, and then everything in the middle we're going to remove until this thing is the next smallest, right? With respect to the sumeressa which beats it, right? So what do we notice? We notice that we don't have to necessarily remove all the elements. In fact, we only remove a suffix of the elements, right? We remove the last few elements that we added. So how many times do we actually have to check or remove elements over all iterations? Well, let's leave that question when we go through the solution. So the solution of this problem is our list needs to support 3 operations, right? The first operation is query the end value, right? In the last value of the list, we need to be able to query it to be able to ask, is it less than our current considered bar, right? Is it less than our current considered sumeressa strength? Then we need to be able to delete a value of the end, right? We should be able to remove this, right? And then iteratively do that. And we should also be able to add a value, right? And that corresponds to taking this sumeressa and adding it into the list once we're done, right? And this sounds pretty much like a stack, right? You can query the end, you can delete a value of the end, and you can add to the end, right? And you want to do this in quick time, right? So L is a stack. And furthermore, L also stores a non-increasing subsequence of strengths in order of index, right? So like we said, what L is going to look like is it's going to look like a set of non-increasing heights, right? Or non-increasing strengths. So it's going to look something like this, right? And then whatever. And then every time we add one, this is the one that we're going to add. Every time we add one, we're just removing a contiguous suffix of the things which are already in L. Yes? So since L always stores this non-increasing subsequence, it has a monotonic property, right? The property is it's always non-increasing. And so we call this a stack in sorted order. L is often called a sorted stack. The other more fancy way to refer to it is called a monotonic stack, but they principally refer to the same thing. And so let's say we just simulate this algorithm using this sorted stack. What is the time complexity? It seems like we're doing the exact same thing we're doing. We just made one other new observation, which is you don't have to look through the entire thing. You only have to look through the last few. But turns out this is actually sufficient to reduce our time complexity. Notably, each element gets check removed at most once, right? Check remove is you check it and it's less and you remove it, right? So every element gets check removed at most once. And that's because once you remove it, you're never going to check it again, yes? And so there are firstly, there are n elements. Across all iterations, each one gets check removed at most once. And secondly, each iteration also checks an extra final element, right? Think about it. On each iteration, you're going to eventually reach a final block, which is going to be greater, right? And then you're going to check it, and you're going to say, hey, that's not okay, right? And then you're going to stop. So each iteration checks an extra final element. So together, there are order n checks and check removals, right? And the way you see this is there are n check removals at most, right, for each element, and then each iteration contributes one check remove, right? So there are n iterations, there are n elements, that's n plus n, 2n, which is order n. Does that make sense to everyone? Why the time complexity is better? Yes. So this is like a term which you might not have heard before, but the idea is even though there are lots of for loops and it seems like we're doing n squared work, turns out using this monotonic stack L, we are able to amortize the solution to O of n, right? Which means across the entire thing, it's going to be O of n, even though the work at every iteration may differ. Yes, does that make sense to everyone? Yep. It's okay. It just means average, kind of.
Over time, it adds up to all.
Yeah.
Amortize means like to help or to like alleviate something.
Does everyone have any questions? Can I move on? I'll expect. Okay, I'll just like assume no one has any questions. Okay, so you guys have all heard of AVL trees, right? So okay, yeah. So has anyone? Wait, like you can eat and listen at the same time. Wait, like those things aren't mutually exclusive, right?
ABL tree, Austin. Austin, ABL. Never heard of
Excellent question.
Actually, never seen an AVO tree in my life.
Whoa.
Thank God. You have been spared.
I'm kidding. Austin,
Yeah.
I don't want to implant an AVL tree.
Unlucky. Wait, didn't we have to do one for the 2521?
We had to implement like one function.
Why are trees upside down?
Huh?
Why are trees upside down?
They're right side up. What do you mean? It's the roots, no?
The ones outside, it's up, the roots are
Yeah, it, like it goes like the
Wait, doesn't it grow into the ground? Like roots, right?
the roots at the bottom. And then they grow up, they branch up.
Ah. I don't know. Computer science students don't go outside often, so I don't think they really know what a tree looks like.
Pizza down
They
there.
also lied about what a DQ was. Apparently it's not a circular ball.
like you're technically not.
Oh, okay.
They take like they take like
Just make sure you clean
fixed size arrays. It's like a map to like different arrays, and they have a circular buffer of these like arrays, like chunks.
Oh, right. So they chunk the element.
You're gonna like no. It's not the one. So a vector, it'll just be contiguous. But the DQ, they don't guarantee that it's like contiguous. So you have a map into like a block of say 4 kilobytes or something like that. The exact size is implementation dependent. And then when you add to it, they'll add like another block to each side like that. So it's like you have more overhead because you have to like dereference the map and then access the array within that.
So it's like a linked list.
Sort of.
If it's not continuous, how can you access the values in O1?
Because you have the map, like you know like they're all contiguous
I think
within that.
they bucket it, so it's like
But
They do, like,
what
bucket.
about like the dot begin and dot end like because I'm pretty sure
they store pointers to every.
You have your map, right? So your map, you can think of it as like this block, and you're like logically separating it. So if you want that index, you just be like, oh, is that like located?
It's to do with apparently when you add or to either end, it doesn't invalidate the previous references to elements. Whereas in a vector it can, because if you resize, you lose the average. So to keep that, they don't want to. That's
Hello. Wait, I promised I'd teach while you guys ate, so we're gonna do the last section of this. Yeah, so you guys can keep eating. Whatever. Okay. Firstly, do we all remember what binary search trees are? Great, excellent. So binary search tree is a tree where each node holds a value, right? And it's such that every node has at most 2 children. First of all, that's where you get the name binary from. And for a given node with value v, its left child has a value x less than or equal to v, and the right child has a value greater than v, right? And that's where you get the name binary search from. And so you might be asking why there are 2 binaries. I don't know. So when the worst case depth of the tree is log n, we say the tree is balanced, right? The tree is balanced because you can walk from the top to the bottom in log n, right? But sometimes it's not log n, right? And so there are various data structures which maintain a balanced BST, and we call these self-balancing BSTs, right? Affectionately, we like to refer them as SBBSTs. But this is only nice when you type it out and not when you say it. So I'll not say it like that. And so you might have already encountered one of these if you did 2521, and they're called AVL trees. I'm sure some people are doing it now. Some people did do it. Some people haven't done it yet. But yeah, AVL trees, right? And so what is an AVL tree? Well, from like a black box framework, they allow you to add an element x in log n, query the min or max in O of 1, query the order of an element in log n, and delete element x in log n, right? Order is like if I ask for example, if I ask what's the index of element 3, it'll be able to find that for me, right? So it's able to do that. It's able to delete element x in log n, right? And so basically, what this essentially does is it maintains a sorted dynamic array, right? You can add things, you can delete things, and you can query where something is, right? Or you can basically do a binary search over it. Crazy, right? So how do we use one in a contest? Excellent question. Let's go through the implementation of an AVL tree. Right, so I picked this up from the Comp 2521 slides, and as you can see, it's somewhat of a trek. So firstly, there are these things called rotations, right? I don't really want to go into this. I did have to practice implementing one in order to sit the exam, unfortunately. Yeah.
Are the images rotated because of the rotate left and rotate right functions?
No, they're rotated because I used a mouse and I rotated them in via image. Yeah. Great. So, yeah. No, this is just one image, and then this is one image. Yeah.
How do you do it?
How do I rotate an image? I have no idea. I have no idea. Absolutely no idea.
You see, that's why you need to use tips. It has a rotate
Okay, so instead of dealing with AVL trees, we are not, this isn't a 2521 course, we don't care, right? We can just use C++ built-in implementation of an AVL tree. Technically not an AVL tree. Technically it's a red-black tree, but whatever. And so what a set does is it basically does exactly what an AVL tree does, right? It maintains a set or a sorted list of unique items. It allows for O of 1 query at the start and end, and log n insertion and deletions. Yeah? And this is how you would use it in C++. So for instance here, I create a set, right? And that's currently empty. And then I'm gonna add 1, 3, and 5 into the set. And that'll look like that. Yeah, yeah? No, it's sorted. Yeah, sets in C++ are sorted. Which makes it really nice, right? For example, if I insert from 6 to 1, it will put them in the correct place, right? It won't just chuck them at the end, right? Which is really nice. I can ask, I can ask what the first element of it is, and I can also find the find where 4 is and erase it, right? All these operations are log n, except for this one, which is O of 1, right? Do we know what the star does, by the way? Yeah, so begin returns a iterator, which decays into a pointer, and then when you star it, you dereference the pointer, right? So you get the value. Yeah. C++ also allows you to store lookup tables, right? And these are called maps. And so they're basically just sets, but they store pairs instead of single elements, right? So you can add key value. So basically, this is like a way that we can store lookup or frequency tables. And basically, you add key value. You can remove a key value. You can find the value stored at a key and edit the value stored at a key, right? It's pretty much the same as a set, right? And the reason why you would use a map over a set of pairs is because getting the value at a particular key in a set of pairs is really hard, right? For example, say you wanted to get what value is stored at 2. The answer is 1, right? In order to get this for a set, you have to do a lot of complicated stuff, right? You gotta to do a lower bound, you gotta do whatever, right? And for a map, all you have to do is call what is the value at 2, right? So a map is like better, right? Factually correct. So if you want to support duplicate values in your set, you actually can, right? And this is through a multiset. And a multiset is just pretty much a set, but it stores multiple elements. And in particular, multiset.find will return a pointer to the first x that it sees, right? But who cares? Because all the x are the same anyway.
No, that's really important. That's caused me many bugs previously. If you want to erase one element, erase multiset.find.
Yes, correct. Please don't erase x. Do not erase x when you're using a multiset. You gotta erase find x, right? Anyway, if you're like a bit special, you might want to use a multi-map. And so what a multi-map is it stores duplicate keys, right? And this is really useful because it removes the entire reason why a map is useful at all, right? Like if you want to find the value at a key, you can no longer do that because there may be duplicate keys. And then so this is really useless, right? But it exists. Some guy spent a couple hours sitting down and implementing this as part of the C++ standard library. No, have you? Yeah. It's terrible. Okay, here's a final problem that you guys can try. This combines. In order to full solve this problem, or in order to solve all subtasks, it combines pretty much all the topics that we covered in today's lecture. And so this problem is called photographs. It's adapted from a LeetCode problem. So if you guys like LeetCode sweats or something, well done. It's 239, right? I don't know what that means. But basically, there's a horizon line, and you can divide it into n segments. And the ith segment has a beauty value, bi. And your camera can take a contiguous range, k, of those segments, and basically the beauty of that segment is the maximum beauty of any segment in it, right? So for example, say the numbers were 1, 2, 3, and I took k equals 2. I took a photo of 2 and 3. The beauty of that would be 3. And so for each photograph, every photograph location, you want to be able to determine its beauty. Does this problem make sense to everyone? So in order to visualize this, maybe I will draw a diagram. What that looks like is you have a set of values, right? And then your camera basically can capture a set or a contiguous range of k values. For example, say you got k equals 3. What this means is your camera can capture from 1 to -4 inclusive, from 3 to 1 inclusive, from -4 to 2 inclusive, 1 to 7 inclusive. These are all the 4 possible locations for a photograph. Yeah? And so the beauty of a photograph is the maximum beauty of any segment, right? For instance, this photograph would be 3. This photograph would be 3. This photograph would be 2. This photograph would be 7. Right? And the problem is basically you want to find all these values, right? You want to print every single one of these values. And you can think about this problem. If you have ideas, I'm pretty sure everyone in the programming port knows how to solve this problem, so you can just ask anyone, right? I mean, half the people here who aren't in the programming pool also know of the problem. So. Oh, really? I didn't do it in no event, so. Okay. I will not spoil this. By the way, there's an IMC coding comp tomorrow. Some people are doing it, like me. So.
Everyone should give the last follow.
Please do this. And also, feedback. Scan the feedback form. Not sure if I added this event to the feedback form. I should have. But scan the feedback